Thank you, Prasad. Can you hear me properly? So you are all okay to, I talk about too much of bottom ash, harvested ash in this Sunday morning, right? Oh, okay. Okay, so I will talk a little bit different. So I will talk about the durability-based performance evaluation approach for the effective use of the uncommon ash. But we spend a lot of time to develop this durability-based approach for the conventional coal ash. So I will talk about that first, and then we'll switch it over to the uncommon. But the data bank at this time is really ready. This technology is going to be implemented pretty soon through the Tech.Field project. But we have less data for the uncommon ash at this time. What we did, this is the exact thing we did. We did a rapid and comprehensive durability-based performance evaluation of cast-in-place high-performance bridge deck concrete. And this approach needs to be applied during mix design or trial batch stage. So all the research that we did, our goal is to give you the practitioner a tool that can be used during mix design and trial batch stage. That means dependency on the long-term durability test. Some of the tests take 56, 90 days, 180 days. Can we minimize, can we design the mix in a very smart way? That's the goal. So, we are covering the 4 major durability. To evaluate a mix, 4 major durability. Number 1 is ASR. Number 2 is shrinkage. Number 3 is the chloride-based durability. Number 4 is the freeze-thaw durability. Individual aspect. I spent personally for alkali silica reaction 13 years of research at Texas A&M University, developed 2 ASTHO standard and 1 performance-based approach. I really need to talk about all those today. I'm just taking the output, the innovative test, the approach here, and plugging to the Excel-based tool and how it helps the real-world people. Similarly, shrinkage, it is not my expertise. There are a lot of good work has already been done. The good models are already available. So I picked up those information with slight modification. Chloride durability, a significant of work has been done based on the formation factor and transport property, resistivity measurement, formation factor, transport property. We did around 5.5 years research fully funded by Texas Department of Transportation to identify some of the gaps, fill those gaps smartly, and come up with a very effective way to use formation factor. We know the formation factor reliability is a big deal. So we spend a lot of time to improve the formation factor. So we collected the available information, we did some work on our own and put it into the tool. Similarly, freeze-thaw durability, we all know freeze-thaw durability, if we make air distribution is good, it is freeze-thaw durable mix. What is the matrix portion without the air void? That is defined by the time of critical saturation, which can also be connected with formation factor. So we'll talk about that. First, I will talk about the conventional ash, and then we'll talk about the uncommon. By the way, this everything is that's what our research with Texas Department of Transportation. We put everything in an Excel sheet. There are fantastic model called thermodynamic modeling is available, but the duty people cannot use thermodynamic model. That's why we did the research. This is the ASR research. That's what I told. This is the summary that how to do, new ash come to you, how to do the optimization of that ash. Suppose you know the aggregate reactivity, how much you need to mitigate that ASR. As this time ASTM 1778 talk about 2 years, and very minimum DOT does 2 years test, right? So you need some quick solution. What we did is a fundamental material properties. I give a lot of importance on pore solution chemistry of a concrete. So I spend a lot of time to do the pore solution estimation of the concrete, not the measurement. Extraction techniques available. How many people do the extraction techniques? Oh, sorry. See, the extraction techniques is laborious and very minimum people do that. That can be used for validation purpose. So what I did is, see the cement, and you know SCM contributes soluble alkali. At this time, it considered inert. That's not a good assumption. Some of the SCM contribute soluble alkali and enhance pore solution alkalinity. We consider that. See here, cement alkali, 75% of the bulk alkali cement come to the pore solution. That's fine. NIST model assume that. That's okay. What about the fly ash? What about the SCM? So we introduced called ASTM, modified ASTM C114 to measure the water soluble alkali. And you know the ASTM C311 available alkali. So there are procedures to measure the soluble alkali from fly ash. So this is, we use water soluble alkali for ASR. It's quick. Whatever crystalline phase soluble is there coming immediately to the water, that we consider for ASR purpose. So we develop a TTI model 1. Okay. So this we combine together, water soluble alkali from cement, water soluble alkali from fly ash, combined together, we estimate the pore solution. Right? So you change the fly ash. If it is contribute high, it will be reflected here. Then we compare with the threshold alkalinity of the aggregate. Aggregate having a threshold alkalinity level, right? This is the research we did, another test procedure, another lot of aggregate we tested, different level of alkalinity. We developed this relationship. These are the aggregate reactivity and these are the threshold level of alkalinity. If the aggregate reactivity is very high, threshold is around 0.3. If aggregate reactivity is slow, threshold is 0.45. So if you know the aggregate reactivity, assign the threshold based on this relationship and compare whether pore solution slightly lower than threshold alkalinity of the aggregate or not. Whatever the percentage of SCM meets satisfy this criteria, that is the optimum dosage to mitigate ASR of that particular aggregate. This is called quick chemical screening tool, very quick. It takes only 1 or 2 days time. Very quick, but based on pore solution, it's fundamental. So this is all Excel solver, everything is done in the Excel sheet, everything is done. You just feed the input, you don't have to do anything. Excel sheet is going to do that. I'm explaining. But the text.people people doesn't have to know this theory. So we calculate the how much you need to mitigate ASR. This is, I presented in several conferences. This is accepted in TRR, last year TRR journal, it is published, so you can go and learn better there. Now, how to use, what is our approach, performance-based approach for ASR? What we do? We apply screening tool, right? And then measure the how much you need. 1567 data is generated by all the DOT. Everybody generates 1567 data. I want to use that data. I compare these two. If the difference is below 5%, you don't need any other test. So I am using the 1567 data judiciously. Is it 1567 doing a good job or not? Screening tool I am using to justify that. If the difference is more than 5%, then definitely you need a concrete test, which is accelerated concrete cylinder test, another astro test that we developed. So this is our approach. This is the accelerated concrete cylinder test. We use 3 by 6 inch concrete cylinder. This is the all mixed design information. The most important thing that we do, we match the pore solution. Whatever the pore solution of the tested concrete, the same chemistry of soap solution is here. And LVDT data acquisition system, we measure the length change of the cylinder, expansion of the concrete due to ASR. It's a very accurate test. It is an ASTO standard, but this test need little costly, right? You need an LVDT, you need making soap solution, and the soap solution is actually our model we used to predict the soap solution and then design a soap solution. This test is very reliable. The advantage is effect of soluble alkali from HCM, this test detected because of the test condition itself, and it can be used to take the job mix test because it's a normal level of alkalinity, and it's all of course 4.5. If you compare 1293, 8.9. So this test, but I am not saying that you do this test all the time. What I am trying to say is you do only very minimum situation. Most of the situation step 1 and 2 will be done very limited. Suppose, and I have an example for that. This is the example. We tested all conventional ash, class C and class F. So I tested around 23 ash. 15 ash, step 1 and 2 is good. Whatever we predicted screening tool, and 1567 and ACCT all are same. So 15 ash, step 1 and 2 within 14 days done. Remaining 8, you need ACCT testing, but within 8 I am recommending only 4 because the difference between 1567 and ACCT, CST is actually 5%, below 5%. But these 4, 7 to 10% difference between 1567 and chemical screening tool. So those 4, you need to do ACCT testing. That's the management. That's the ASI. This approach is implemented for TextDot. I have been testing multiple sources of HCM for TextDot for the last 4.5 years. This is implemented. For shrinkage. Shrinkage is, what we did. You give the input of the mix design, 28 days compressive strength, aggregate property, binder proportion. In addition to that, you give the input of 157 information, the shrinkage. Then we use B4 Riley model. It's very good model. Why we selected this model? Because it predicts autogenous shrinkage, it predicts the drying shrinkage, it also predicts the cracking potential. So we use this model, this input, it predicts 28 days autogenous shrinkage, drying shrinkage, and cracking potential. Cracking potential work, of course, they did a good job here. So we use the way, because cracking potential, your compressive strength, tensile strength, modulus of elasticity, and creep coefficient needs to be there to do a good way to do the cracking potential. So this model works really well. This is inbuilt in the Excel tool, and we still need validation. We still need to measure autogenous shrinkage, drying shrinkage, and cracking potential based on actual value. What about the resistivity? The biggest resistivity, significant amount of work has been done by different researchers. A good work has been done. What we noticed is that resistivity based decision is a classification, but we need to go to the next step. Classification means what? That means resistivity need to be converted to formation factor. Formation factor is a fundamental way to characterize the transport property of concrete. We understand that formation factor, this is there is a formula, concrete resistivity by the pore solution resistivity. The pore solution resistivity play a very important role. So we spend a lot of time to improve the formation factor. If you improve the reliability of formation factor, you can use that concrete transport property, and then every performance indicator you can do it. So our work is, so here, these are so in the Excel tool, hydration model is already there, equations are already there. So it model the hydration behavior depending on those input. Now, this is very important. We develop called pore solution model 2. We estimate pore solution. It considers soluble alkali contribution from cement, silica fume, and fly ash. It also alkali binding, because whenever the pozzolanic reaction due to addition of HCM, it produces hydration product with calcium by silicon ratio lower than the normal hydration product for the Portland cement. And when the calcium silicon ratio goes down, it binds alkali very effectively. So that is incorporated in our model. We collected all the good work. This is the alkali binding. They did extremely good work. So we use their work to introduce the alkali binding in our model. And also the model parameters, James thermodynamic, we extensively use James thermodynamic modeling to validate. If you go to the net, this is the most important step, that if you want to do resistivity test, what kind of curing and what kind of conditioning, that's very important. We spend a lot of time to develop that. This is a backbone of our work. I'm giving the summary of couple of years research. What we did is, see the pore solution chemistry of the different mix. This is cement and 6% silica fume mix. Class F ash 25, 20% class F 5% silica fume and 35% class F ash. This is class C ash 35, 29 class C 6% silica fume, 35 class C and 10% silica fume. You see the pore solution conductivity. We calculated pore solution concentration and used the classical equation to convert it to conductivity. And these are our estimated pore solution conductivity. We didn't do any test. It's estimated. You see here, this is the standard pore solution curing according to the ASTM-C 1876. The 1876 fixed the value. If you fix the value, SPS, this is the formation factor calculation, that means denominator is fixed. If denominator is fixed, then formation factor loses its importance. Simple thing, everybody understand that. How to make formation factor case sensitive, mix specific. If you change this, you need to change this, cannot be fixed. This is the work we did. Now, class C mix for 30 to 40% higher than the conductivity assigned by ASTM 1876. We realized that means class C mix, you cannot use standard pore solution curing. You cannot. You have to use average of these three, right? So we did extensive testing. We did average of these two for this, average of these three for this, we did average of this, and then also we did testing SPS, compared the data. It's a huge experimental program. We thought that let's make it practical for the real world people. If I am telling you, make a soak solution for this one, soak solution, whenever you do F, soak solution 2, class C, soak solution 3. I cannot do that because real world people need a solution. So what we did is, based on our research, we just did 2. You see here, if the pore solution conductivity, if it is 67 to 91, if it is yes, then use the ASTM 1876 standard pore solution curing is okay to do that. If this is not satisfied, you have to do matching pore solution curing. Just do. Improving the reliability of formation factor. And you see the beauty, I have a slide. Now I can use formation factor to evaluate performance indicator. Beautiful, nice way. Okay? So this is the situation. Now, so you took a decision, right? And then you come to another one, which conditioning? Texas DOT told, we cannot wait 91 days. Simple. Can you improve? Can you save time? That was my challenge, right? I cannot say 91 days, no, they are not going to accept it. AC1, AC2, 28 days, as to TP119. AC2 means you do 3 days at 23 and 25 days at 50 degrees C, it's acceptable. Or AC1, 7 days at 23 and 21 days at 40 degrees C. AC1 is well established, precision statement is probably done. AC2 has not yet reached that stage. But AC2 can be universally considered for all, but it may take a little time. So, okay, so we are defining whether it's MPS or SPS. We are defining whether AC1, AC2, and then you do the resistivity testing. Then you convert it to pore solution. So whenever you are doing SPS, use the SPS as a pore solution resistivity. When you are using MPS, use the pore solution resistivity of MPS. So denominator is changing, numerator is very reliable, formation factor is reliable. Now next step. So you did a good job here, resistivity to formation factor. We have inbuilt chloride isotherm is inbuilt in the Excel sheet. So everything is very well defined. Now these are the exposure and construction input. what is the chloride loading, what is the construction input, location and month of construction, and designing service level target reliability index. These are all input. You see here the input, resistivity, see the curing MPS, AC2, actual value of resistivity, and the measured resistivity. Okay, and then these are the all chloride exposure condition. Those are surface chloride, rebar depth, rebar type, corrosion inhibitor, Amarillo, Texas, July, and target reliability index is 1.3, and we need to achieve the 86% of degree of critical saturation. How much time it takes? See the output here. Resistivity based is 45, very low. It's a measured saturated resistivity. Of course, we do saturation correction factor. We do separate experiment that is inbuilt. Saturation resistivity is this, very low. Apparent formation factor, very low. Saturated for, so you are giving a classification and actual value. But how to use that? We go to the next level. Next level is this: apparent diffusion coefficient, chloride binding factor, effective diffusion coefficient, estimated time of corrosion repair, probability of failure is sharp model, and the reliability index 1.685. Is it pass or fail? That's, and then for the degree of critical saturation, FT service is how much time it takes to do the critical saturation is 42 years. So these are the outputs. Now, so these are all input goes and output, and you don't have to go through all the equation. That's for just equations are already inbuilt. These are the classical equation. We modified. We actually introduced apparent formation factor based diffusion coefficient here. We use concrete cover is here, and aging component exponent is also very mix specific situation. So because now formation factor is connected. Similarly, the degree of critical saturation, formation factor based reactivity is one of the input is created here. Degree of saturation, everything is. So these all are inbuilt into the Excel tool. Now these are all theory little bit, right? Now excitement is case studies. So this the tool looks like. Everything is connected. See you give all the input, it predict how much SCM you need to mitigate ASR, what is the autogenous shrinkage, drying shrinkage, and cracking potential. Then it select the resistivity testing parameter. It calculate formation factor. It consider all the exposure conditions, and it give the time of corrosion initiation, probability of failure. It also time to critical saturation for FT durability. So everything is in Excel. Now I applied this. We applied this for the real world application. This is interesting for everybody. You see here, this is the bridge deck concrete in Galveston, Texas. It's less than 1 mile from the ocean. Okay. They use 25% AFS mix. They call HPC. And TexDot asked, given the job, can you tell me whether it's an HPC or not? High performance concrete mean what? High performance concrete doesn't mean a strength value. High performance concrete means it has to withstand the challenge of the environment in that particular area. Now, we applied, the tool predicted shrinkage is low. We measured also low. Now, resistivity formation factor. These are the CL means low. Those are the values, the classification. The most important thing, the chloride binding factor is also coming. Effective diffusion coefficient measured, predicted by the tool. This is the measured value. Now focus here. It says, according to the time of rebar corrosion, more than 75 years. It doesn't, that value doesn't mean really anything, right? You need to go here. The probability of sharp model, probability of failure, saying 17%, the value is 0.94. Okay, the value is supposed to be 1.3. 1.3 is kind of standard value recommended by Sharp. It is low. Probability failure is high. Red flag, it failed. As far as the chloride performance is concerned, it failed. Tool is telling it failed. So we went to the field and checked the bridge deck, and we took a bunch of core, and you see they use black steel. No epoxy coated steel, and CNI dosage was I think 2 pounds per cubic yard gallons. So, and you see the surface chloride up to 2-inch depth is very high. So the chloride concentration is high. they use black steel, mix failed, transport property failed, and corrosion occurred. So it's a proven case study, right? Now go back. They told, what is your suggestion? I told 25% FS mix is not high performance concrete in Galveston. So I told, okay, let's modify the mix design. So we modified the mix design by adding 5% silica film and 20% FS. Shrinkage, of course, shrinkage, cracking potential increased a little bit, but it's still below the 1.5 limit. It's still low to medium, but little bit potential increased because silica film added. Now transport property, probability of failure is extremely low. This value is 2.14, is above 1.3, the index value, it passed. See here, that's the tool is predicting this. And it takes only 28 days time. Tool is predicting the mix design behavior under a particular geographic location, under a particular exposure condition. What are the recommendation? You use this mix, but this mix is going to increase the cracking potential a little bit. Make sure you place the concrete in a right time of placement. You know, the wrong time of placement introduce thermal gradient and thermal strain. Concrete works predict that, which is not part of that. So if you do a good job, good curing, it should be fine. Now the second example, this is Amarillo. They use 20% Class C and 6% silica film mix. They told, is this mix good? Is it high performance? So we applied our tool. Tool predicted cracking potential moderate to high, 1.32. We actually measured 1.4. This is relatively in higher side. 1.5 is the limit. So it is gradually approaching the high. Cracking potential of this mix is high because of high autogenous shrinkage. That was not the consideration of TXDOT. TXDOT says drying shrinkage, all the mix packs drying shrinkage, so they are okay. But high performance bridge deck concrete truck ticket shows use of 0.39 water cement ratio. 0.39 water cement ratio with silica film is going to introduce some amount of autogenous shrinkage, which nobody considered. So autogenous shrinkage is little bit high. Okay, now they place this concrete in a 4 to 7 a.m. very peak summer time. It in concrete work says that it introduced some thermal strain. So autogenous strain, thermal strain, a little bit drying shrinkage combined together, concrete strain, total strain is higher than the tensile strength of the concrete at very early age, before 7 days, and concrete cracks. Verified by petrographic examination. This is a classical example that this mix why cracks, because of the wrong time of placement. And autogenous shrinkage was, TXDOT was, wait a minute, we have to, autogenous shrinkage, we don't know, but it is important, right? So it explained it's very much explained the actual case studies of this approach. So this, but what about transport property? Fantastic transport property. See here, 8%, 1.42 is pass. So transport property is okay. ASR is okay. You are using 29 plus 6% silica film. Fantastic ASR. You don't need any concrete testing. So ASR done. Transport property, freeze the durability, everything is okay. But shrinkage, cracking is a red flag. See, you are considering all the 4 durability aspects at the same time. Sometimes focus on ASR. What about other 3? Sometimes chloride too much. What about ASR? All 4 needs to come together. This is a good example. So basically what we are recommending, this mix still works, but make sure that your time of placement is selected properly. You don't introduce any extra thermal strain. It should be okay. Okay. So how many minutes I have? Okay. So these are the all non-conventional as, actually, all non-conventional as. I'm just trying to see that if our approach is okay, we don't have much data, but we will talk about characterization first and talk about little bit anticipated prediction. These are all classical, I'm not giving our importance, XRF, 618, XRD, everybody knows, right? So we did everything. For bottom mass, we got 2 bottom mass. XRD, amorphous content, crystalline phase. Good important thing is we need available alkali, right? We need, this is 618, Dog-Hutton's presentation, you all attended that. As long as you maintain fineness, LOI, moisture content, they perform like a class bottom ash, like a class F ash. I have the similar observation. You see here, one important reclaimed ash, LOI is low. Still, foam index you need more. That means LOI test doesn't distinguish between unburned and activated carbon, so some extra thing may be needed. For bottom ash, grinding is of course needed, and high LOI of course needs to be fixed. Otherwise, it will be an air issues. Those are all everybody. You know, everybody talking the same thing. Now, okay. Did I mention the available alkali? Okay, see the reactivity. We did, of course, we did reactivity, and one of the blended ash is here. Remaining ash is kind of class F. Reactivity is similar to class F. Now, ASR, similar conclusion. So we applied our staining tool. This ash is a blended ash, 50% class C and natural pozzolan. It almost behaving as a class C, so it needs more. Staining tool says 45%, ACCT 35%, exceeding 0.04 limit. So you need around 40%. The remaining blended ash, reclaimed ash, two bottom ash are similar as if a class F ash. So yeah, similar conclusions. If you do a good job, 618 criteria, it should work like a class F ash. This is probably last slide. Prediction. Our test, resistivity test is still going on. I thought that I will be able to generate the data and show you, but it's still under progress. So, but we already said that this particular blended ash need MPS curing, AC2 28 days resistivity. Remaining are all SPS, AC2 28 days should be fine. This particular, we are anticipating that little bit of silica film together ternary blend will work fine instead of binary. But this particular blended ash, this is our interpretation, because the reactivity is kind of low, and so we are anticipating that adequate chloride durability may not be satisfied. But these two bottom ash, reclaimed ash, it should behave as if like a class F. That's what our anticipation. We will validate it after actual measurement. And these are all sponsors. I acknowledge them. Texas Department of Transportation is my main funding source, and there are other funding sources and supply of the materials. And thank you.